Hi, my name is Asher and my partner is Nick, and our topic is Diver's Law.
Diver's law has technically never been discovered. It is also known as the no-name law. This law talks about a given relationship between amount and temperature when pressure and volume are held constant. It also states when the amount of gas in a container is increased, the temperature must decrease, and vice versa. When the amount of gas in a container is decreased, the temperature must increase. Suppose the amount is increased. This means that there is more gas molecules, and this will increase the number of impacts on the container walls. This means gas pressure inside the container will increase since the volume is constant. However, this cannot be allowed since pressure always remains constant. Lowering the temperature will cause the molecules to move slower, thus lessening the impacts on the container wall and reducing the pressure to the original value. Amount is measured in moles and temperature can vary. This experiment or scenario must happen in an enclosed hard container so that pressure can stay constant. The mathematical formula for the no-name law is N1T1 equals N2T2. This basically means when there is amount temperature which equals N1T1 changes, then it is equal to N2T2. Now here's an example problem. Now we're going to do an example problem. Let's say a hot air balloon is filled with 118,000 moles of air at 20 Celsius. If the air in the balloon is heated to 98 Celsius, how many moles of air will now be in the hot air balloon? So we're going to set it up in the N1T1 equals N2T2 equation. So it's going to be 118,000 moles times 293K equals N2 times 371K. This is going to equal 34,374,000 equals N2 times 371. Then we're going to divide 34,578,000 by 371 to find N2. Once we find N2, it is going to equal 93,191.4 moles of air. That is how you do this problem, and that is how you use Diver's law.
Okay, so now to demonstrate Diver's Law, we're going to be doing an experiment known as the Cartesian diver. In this experiment, you're going to need a pipette, a cap, and a bottle that the pipette can fit in, as well as water.
Step one, you're going to fill the bottle up all the way like we have done. Second, you're going to take the eyedropper and fill it up so that it just barely floats.
Right now, I'm going to demonstrate why you need to fill up the pipette to where it barely floats and how this experiment doesn't work if you have an empty pipette. So if you put the pipette inside of the water, it floats, it stays up. Now when you cap it off, it's still floating. In this experiment, when you squeeze the bottle, the pipette goes down, showing the change in pressure. But if you notice, when I squeeze this with full force, it still stays all the way up. Now, as you can see up here, we have the dropper that barely floats. And what we're going to do now is we're going to squeeze it and the dropper is going to go down. Now, this bottle isn't exactly the clearest, but if you look up here, you will see the dropper float down to the bottom of the bottle. And here we go. Here, we are demonstrating the change in pressure. When we let go, it floats back up. Now I'll give you a quick rundown of what we just did in this experiment. In this experiment, we see what happens when the pressure on a gas increases and decreases. When you increase the pressure on the outside of the bottle by squeezing it, the diver moves downwards, or the dropper moves downwards. The release of pressure causes it to float back up. What's happening is there's air bubbles that are being forced into a smaller space, making the gas more dense and then causing the diver to sink farther. When you release the bottle, as I just said, the air expands, it becomes less dense, so the diver decides to rise back up.